Welcome everybody. This is the second session in Lie Algebras by Professor Sachin Sharma. So from IIT Kanpur. So very happy to introduce him, and he will be talking about root systems. Over to you, Sachin.
Okay, thank you, Amit. So let us begin. So today's lecture, as we have seen some of the basics of, not I should say basics, but some of properties of from the definition to the semi-simple Lie algebras, the properties of the Lie algebras, and studied by seeing some examples, like basic examples, like Professor Shraddha introduced yesterday's, which SL2, which plays a pivotal role in the theory of Lie algebras. So today we will see an object which eventually determines there are all semi-simple Lie algebras, more precisely a simple Lie algebras. So this object actually obviously plays a crucial role in classifying the Lie algebras, simple Lie algebras. But as it is interesting in its own right to study its own properties, as it is a combinatorial object, and we will see that we can study that object without reference of Lie algebras. So that's how we will start today. Is chapter 4 to 6, Lie algebras and Lie groups. Lie algebras and Lie groups. Of course, we cannot leave Humphreys also. So one can read actually Humphreys, but the advantage of Bourbaki is that it starts from the very basic setting. And yeah, so let us begin. So what are these objects are? So we will begin with let V be a finite dimensional vector space over R. Okay, so we will fix our base field as R. Then there is a very nice linear operator on the space V, so which is called as a reflection. So recall that what is a reflection? A reflection on V is a linear operator on V which fixes a pointwise, means that it is identity on the operator, and maps every vector V which is orthogonal let us say the top hyperplane H, orthogonal to H to its negative. Okay, so what is it? So to define a reflection, we need two data, one hyperplane and and a vector orthogonal 8. What do you mean by hyperplane? Does everybody know? It is just nothing but a codimensional one subspace. Okay. So you will have, suppose alpha belongs to H. So you'll have S alpha of H, which defines on X is equal to X for all X belongs to H, and S alpha of H of alpha is equal to minus alpha. Yeah. So this is what it is, a very nice linear operator. Note that suppose you want to define one wants to define, so let f be a functional, f belongs to functional such that kernel of f is equal to h. So one can again, instead of these things, you can write S alpha of f and define on V as V minus f of V of alpha. Okay, that makes completely satisfying, as you will see that if V belongs to H, that would imply that f of V is equal to 0, and so S alpha of f of V is equal to V, and obviously so here you would like f of S of alpha of f of alpha to be minus alpha. So what you should expect value of f on alpha? So it should be f of alpha. So it's given a scalar. So these things, but as we want these things to have negative, so suppose f of alpha is equal to 2. Okay, fine. So that's what we need. Yeah. So these reflections plays a very important role in the definition of root system. So meanwhile, so let us worry about this, the next lemma, this proposition or lemma, which is very important. So let phi be a finite set which spans vector space V over R. Suppose all the reflections S alpha, I will just denote hyperplane here, S alpha leaves, suppose all the reflection S alpha leave phi invariant. Note that phi is a finite set which spans vector space V over R. Okay, so V is a finite dimensional vector space. Okay, let sigma belongs to GLV. These are all invertible transformation of these things with the property that sigma of phi is equal to phi, and fixes a hyperplane P of V and sends some non-zero vector alpha of phi to its negative. Then you need to prove that sigma is equal to S alpha. So then it is this thing. So it is characterized by the property that suppose you have sigma fixes some hyperplane and leaves alpha invariant and alpha maps to these things. So this you can't have any other, but it should be the reflection S alpha. Okay, this lemma will play a very important role. So we will prove it. So feel free if you have some doubt to stop me. Okay. Yeah. So in case if you have doubt to stop me, there would be no problem. So yeah. So let me start the proof of that result. So how you will go through? So what you have is suppose we prove it is enough to prove that sigma of S alpha is identity on V. Okay. Would it be suffice? Why it will be suffice? Suppose I prove that thing, then what will it imply? Anybody from audience?
Inverse.
Yeah.
Yes, reflection has own inverse.
Yes, because reflection it's of order 2 thing, right? Isn't it? As S alpha is S alpha inverse. Okay. Right. Yeah. So now we know that S alpha. So let P alpha be the hyperplane which is perpendicular alpha. Then we have S alpha of x is equal to x for all x belongs to P alpha. Similarly, sigma of x is equal to x for all x belongs to P. Okay. Now, consider the quotient space quotient V or R alpha. Okay. So note that. So why we are considering V or R alpha? Because on alpha, sigma of S alpha of alpha is just nothing but sigma of minus alpha, and sigma maps again these things alpha. So alpha on R alpha, sigma S alpha is an identity. Okay. So consider the quotient. Yeah. Now let x bar belongs to V or R alpha. So that's x bar will have the form x plus R alpha. Okay. Now, as you have V, you can write down as a P alpha direct sum R alpha, and we also has decomposition P direct sum R alpha. Note that given a vector space, you can write down as infinitely many times these direct sum computation. So we'll have x is equal to x1 plus some c1 alpha, where x1 belongs to p alpha, and x is equal to x2 plus c2 alpha, where x2 belongs to p. But then x plus r alpha is equal to x1 plus c1 alpha plus r alpha, which is equal to x1 r alpha. And this is indeed by the similar thing, it is equal to x2 r alpha. Okay. So I hope this is clear to you, or let me write down one more step. Okay. Now what happens is that, so this is indeed, so consider sigma of S alpha of X R alpha. This you can write down by our thing. This is nothing but X1 R alpha. This yeah, so you see, as this is your space is invariant, that's how you are this quotient space, these things. So this is sigma of S alpha of x1 R alpha, and this is just nothing but, you can see that this is just nothing but sigma of x1 R alpha. But this you can again, you could have started with x2, and this is nothing but R alpha, and so this is x2 R alpha. More precisely, what I am saying is that this will have what I am trying to say here is that this sigma of S alpha will act as an identity on this quotient space. Okay. So what does it means that, so suppose it acts on these things quotient space, and so suppose you take any basis of, so you would like to write down matrix. So suppose if we write down matrix of sigma of S alpha in V, so what we will have, it has form. So suppose let V1 R alpha Vn minus 1 R alpha is a basis of E over R alpha, then V1 Vn minus 1 alpha is a basis of this is, again I am confusing with, this is your V, not E. This is your V vector space, ambient vector space is V. This is a basis of V, and what will be, so the matrix of, so I would choose the order of basis as alpha V1 V2 Vn minus 1. The matrix of sigma S alpha, and this matrix, this ordered basis B, will be 1 0 0. There is some C1 0 0 0 dot 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 this one. Okay, so this will be a matrix. So far, any questions related to it? So basic linear algebra. So I am giving every possible details to you. Yeah. And so I'm sorry. Yeah. So what will be its characteristic polynomial? Yeah. What will be it? Anybody? Characteristic polynomial of sigma s alpha. Audience?
X minus 1 to the power whatever the size of the.
It will be these things. Okay. Yeah. And so it is, so the minimal polynomial of sigma s alpha divides x minus 1 raised to. But sigma s alpha, minimal polynomial of sigma s alpha also divides some other polynomial. Can one guess that? What is the property of sigma s alpha? What is its order, by the way? Sigma s alpha's order? Is it a finite order?
So this is diagonalizable. So the minimal polynomial would be x minus 1.
Why it is diagonalizable?
Sigma square equals to identity.
No, who said sigma square is identity? Sigma is
No.
anything which fixes phi. Okay. Sigma
So this should
is
be an order 2 element, right?
Sorry, S alpha
This
is
would be an
order 2 element.
element.
Sorry.
S alpha, right, sorry.
No, go ahead, go ahead. I mean, like, at least somebody is responding. See, you see, this is the basic linear algebra. I expect people to participate. Do you see that? But sigma S alpha is
on R alpha, sigma compose S alpha is identity. So that means x minus minimal polynomial divides x minus 1 list.
no. On R alpha, no. On V you should have. You understand?
Oh, okay.
Be careful. But sigma S alpha is a finite order linear operator. Why it is so? First of all, from anybody from you can guess that sigma is a finite order map.
It permutes phi because it sigma of S alpha takes phi to phi.
Take phi to phi, right?
Yeah, and phi
But
is
why it is
finite.
finite order then?
Phi is
No,
finite.
it takes the basis to the base. It permutes the basis. The way the basis was chosen, hence it would be finite order, right?
You see, the answer what I want is not coming. So it fixes phi. But what is phi?
Phi is finite.
Phi is finite, but it is not the killing thing actually. Phi is finite, but phi also spans
Yes, spans to.
Okay, that is a very crucial thing. And so suppose a subset spans V and this sigma is a permutes that thing actually. So there will be finite set of phi which will be a kind of enough to these things. So it should be the S of cardinality of phi actually, right? Isn't it? That map, isn't it? So that is the thing. So that's why sigma is a finite order map. S alpha is a finite order map, and product is also a finite order thing. Okay. So this is sigma as, and phi is finite. So is the order of sigma. And so the product of two finite things actually, again, it's a group anyway. So this is, you have a finite order automorphism. And so what do you see? If you have a linear map which has a finite degree, then what about its minimal polynomial?
So
Let me ask, yeah.
So then we'll be having that sigma S alpha powers, whatever the order is identity.
Yes. And then
So
what?
the minimal polynomial would have to divide something like x power k minus 1.
Very good. So the minimal polynomial of sigma S alpha divides x raised to k minus 1. But it divides x raised to k minus 1 and it divides these things. So what should be actually?
Just x minus 1.
Because the GCD of those both things so you are done, right? So this was a crucial thing anyway, but taken a good chunk of my time, but it's important as it involves a basic linear algebra, which is a backbone of literally every mathematics subject. Okay, fine. Now with this thing, I will define a crucial object, root system of our thing. A subset phi of the Euclidean space V is called a root system in V if the following axioms are satisfied. First, phi is finite, spans V, and does not contain 0. If alpha belongs to phi, then R alpha intersection phi is nothing but alpha minus alpha. So the only multiple of alpha, they are the roots, which are nothing but the alpha and minus alpha. If alpha belongs to phi, the reflection S alpha leaves phi invariant. And the fourth one, okay, which is important, that see, for every S alpha, you write as, this is your definition, V minus f of alpha of V. So this f is a special V star such that f of alpha is equal to 2 and f of h is equal to 0, the hyperplane. Okay, so I call that special f as alpha check once and for now. Okay, so this is alpha check, this is an element of V star. Okay. So given every alpha belongs to phi, you will have an alpha check, an element of these things. So you will have alpha check of beta belongs to Z for all alpha beta belongs to phi. Okay, so this is a very crucial property. This is we will soon determine what is that number. Okay, so an extremely crucial property is that this, in fact, this simplifies, this reduces the classification problem to great deal. I mean, that is so this is the thing that I hope the definition is clear. In case if you have doubt, please do not hesitate to ask. The first condition is that phi is finite and spans V, okay, and does not contain 0. Second is that suppose you take the subspace spanned by alpha and you take its intersection, then its intersection will be only alpha and minus alpha. Okay. And the third one is it leaves this reflection invariant. Okay, S alpha, this invariant. In fact, if one wants these things, you can write S alpha alpha check, because every reflection you have with respect to, so this is, I want to say that S alpha alpha check, this is actually your functional F. So this is just nothing but your alpha check of alpha. This is what you have. This leaves your phi invariant, and alpha check of beta belongs to Z. Okay. So fine. So why don't we start with some of the examples to start with? Suppose dimension of V is 1. Yeah. Then what can you say about the phi? This is dimension of V is 1. This means V is R. Okay. This is 0. What do you expect? How does what will be the form of phi?
Just two elements, alpha and minus alpha.
Very nice. These are. There is no chance of having another one, actually, right? Yeah.
Yes.
So this is example 1, and that actually kind of completely does these things. I mean, like exhaust the case where dimension of V is 1. Suppose dimension of V is 2, that is V is R2, and the inner product is standard inner product on R2. Okay. So what do you expect? What is the basic thing? Anybody?
AXY case,
Huh?
AXY plane case, AXY case. I mean,
We can take standard basis and their negatives. Standard basis and their negatives.
Standard basis and their negatives.
Means 1 0 and minus 1 0 and 0 1 and 0 minus 1.
Very nice. So this is, let us say it is alpha. Okay, 1 0. And so you should have minus 1 0, right? Isn't it? And then you take 1 0, which is nothing but the beta, and you'll have minus beta. Sorry, this is 0 1. This is a 0 minus 1. Does it satisfy all the properties? Obviously, it satisfies all the properties, right? So suppose you have S alpha of beta. So what is so first of all, what is the alpha check here? Can you determine alpha check? What will be the alpha check? Note that here standard inner product is given.
2x, right?
See,
2x.
with respect to that, you need to understand that here you can identify, this is a very nice, so this is a standard, so we can identify R2 star with R2 with respect to form, right? So first of all, I need to.
So with this alpha check should be twice inner product with alpha, right?
Alpha check should be
2 times
so
inner
first of
product
all,
with alpha.
let me these things. So suppose everybody knows here what is a non-degenerate bilinear form.
Yes, sir.
Huh? A bilinear form. Let V be a vector space over R or F actually, or R. This is fine actually. I'm taking these things. A bilinear form on V, bilinear form. I hope everybody knows bilinear form, right? Yeah. Do you know bilinear forms? I mean, like, say frankly, if one doesn't know. So I will assume maybe in tutorial one, Ritesh can help you out. Is
People raised hands. Yeah, so
okay.
Therefore I think they know. Yeah.
Okay, good. So a V via vector space over R, a bilinear form on V is said to be non-degenerate if
zero
for
vector is the
sorry,
zero vector is the only vector orthogonal to all vectors.
right. So if V of V dash is equal to 0 for all V dash belongs to V, he said it perfectly. 0 vector is orthogonal to all those things. Then that implies that V is equal to 0. Okay. Yeah. That is the thing. Now, this is a very crucial property. So suppose you have this property, then what it makes is it makes you to define a map phi from V to V star. Okay. So usually the morphism or isomorphism between V to V star is a basis dependent, but due to this, you will see that now how we will define a map. Phi of V is equal to this form. This is dot. This is a notation which you will often see in this course of lectures. So what is this V dot? This is a functional. This belongs to V star. Okay. It means that it is a mapping from V to R. How it is defined? V dot of some W belongs to V is equal to, this is a definition. Yeah. Okay. So that's what your thing is. And exercise. Prove that this is indeed a isomorphism from V to V star. Okay. Why it is an isomorphism? So first of all, it is a linear map. Everybody agrees, right? Why it is a linear? Because phi
It is the inner product.
is bilinear, right? So it is a linear in the second component, right? So that is the thing. And first of all, why this phi is 1, 1? suppose phi of v is equal to 0. That means that this operator v dot is 0. That means that v of w is equal to 0 for all w belongs to v. But this will be possible only when?
V is equal to 0.
Because?
Non-degenerate.
Because of the non-degeneracy. This is extremely crucial, this will be a tagline for the coming course to play. So this is a basic fact which everybody should know about this. Okay. So fine. Now using that thing, and now you know the form. Does anybody know that what will be the alpha check? Now you come back to these things. V is equal to R2. Okay, we have a standard bilinear form. You will have this root system. Okay, check this is a root system. Find alpha check and beta check using the non-degeneracy of your standard bilinear form and prove that it is the root
Take
system.
the fact that if V is a vector, then it goes to 2 times V inner product of V and alpha divided by the norm of alpha square.
Yeah, good. I mean, like, so I believe this is a very easy thing, and we can deal with in the these tutorial sections actually. Okay. Now I will come up with another thing. Again, we will have V is equal to R2. I will take my alpha 1 vector, unit vectors I will take actually. Okay. This is alpha 1. Then I will take another vector which has a degree 60 with it. A unit vector, alpha 2, 120, alpha 3, 180, okay, 240, okay. So there are 6 things. Yeah. Now the question, anybody knows this thing? Like, would like to answer? Is it a root system?
Yes.
Yes. Why?
No,
What is? Why it is so?
No, this is not a root system. So here, I mean, if
so this, see, these are not any roots actually, by the way.
yeah, this would not be a root system.
No, this is not actually. This is, there are only 6 things in these things. So I just don't get confused with that line. Okay. Alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6. Okay. This
What is the
just an
angles over
axis.
here?
60.
60 degrees, then yes, it's a root system, right?
Right. Why it is so quickly, as you said that? What is the special about 60?
I mean, once you have put that integer condition over there, then the 60 degrees would be forced over there, right?
Yeah. So
I mean, so the last condition would force it to be something like this.
Again, you need to use the bilinear non-degeneracy of the bilinear form. of bilinear form to find an all alpha checks, alpha 1 check, alpha 2 checks, and alpha 6 checks, and prove that alpha I check of alpha j check, alpha these things belongs to Z. This is again, we can do it in the tutorials if time permits, but I leave it to you to determine alpha I checks, okay, using the non-degeneracy of the bilinear form. Yeah. So like this is a 1, 0. What will be this vector alpha 2? This is cos 60 sin 60. So what is the cos 60? 1 over 2 sin 60 root 3 by 2. Similarly here, just kind of reflection of those things, and you will see that these indeed satisfy these things, and this is known as the root system A2. Okay, so fine, as far as we have started our things, those things, the main thing of the checking is to determine what is the alpha check, alpha I check. So we will do it in this these things. So here is the proposition which kind of fixes this problem of determining alpha check for all, once and for all. Here is the proposition. Let be a symmetric bilinear non-degenerate so before giving this proposition, I will define a crucial group. Let phi be a root system a subgroup, a group. If I write V phi is a root system, means that V is a finite dimensional vector space over R, and phi is root system, a subgroup generated by all S alphas. Alpha belongs to phi. It's called Weil group and is as W of phi, or simply W if there is no confusion. Okay, so what about this group? Is it a finite or infinite?
Finite.
It's finite because
Phi we are taking is finite.
and
Generators having finite order.
yes, but if you know any finite group which is contained inside, any group which is contained inside,
It is contained inside the permutation group, right?
permutation group of what?
So if you look at the permutation of all the roots,
That is very important actually. Yeah. So it is a contained inside S of phi, S of cardinality phi, right? Isn't it? Which has a cardinality phi factorial, right? So it is a contained in, so it is a finite group. Okay. So this is the thing that this is a finite group. Okay. Now here you are. Is the lemma. So let be a symmetric non-degenerate bilinear, symmetric, not needed, it should come later. I will explain this. W phi invariant form on V, then alpha of alpha is not equal to 0 for all alpha belongs to phi, and the isomorphism phi from V to V star given by phi inverse of alpha check is nothing but 2 alpha by alpha. Okay, things to pause over. What mean by a phi is W phi invariant? Anybody who knows?
Invariant under the operator.
Yeah, a bilinear form said to be W invariant if sigma xy is equal to xy for all xy belongs to V and sigma belongs to W. Is it clear? What does it mean that? So this property you have seen somewhere. Sigma xy is equal to xy. Which operator satisfies this property? Linear algebra? In the inner product, you have seen something like that, right?
Orthogonal operator.
Right. It is like a distance preserving property, right? Isn't it? Yeah. Norm of T of x is equal to x, right? Norm of x actually. So this is the thing. When you say sigma xy is equal to xy. Yeah. Now we would like to show that this is, see, this is the basic assumption. If you go Humphreys, this is actually Bourbaki stuff. If you go Humphreys, he directly assumes positive definiteness and start with proving it. If your form is positive definite, everything actually falls in a pieces. So, but here you start with the basic things, like you assume the lower hypothesis, like non-degenerate, non-degeneracy. Being a form is a positive definite is a very strong condition, but every inner product, every finite dimensional vector space over R has that property. Okay, so this is the thing. So let us try to prove it. Consider S alpha of beta, sorry, which is by by the invariantness, this is alpha beta. This is, you have alpha minus alpha check of alpha, alpha, beta minus alpha check of beta of alpha. This is equal to alpha beta. Okay, so where here alpha and beta belongs to R, sorry, phi. So this is minus alpha beta minus alpha check of beta of alpha. This is equal to alpha beta. Now, what is the next thing?
We expand it out. So
Now suppose contrary, that alpha is equal to 0. Okay, we want to prove that it is non-zero. So what will happen? The left hand side will become 0, right? Isn't it? What will happen? Yeah, so this is 0 anyway, so you will have twice of alpha beta. This is equal to 0, and alpha beta is equal to 0 for all beta belongs to R. Can one complete the proof now?
So we have taken beta belongs to phi.
Sorry, beta belongs to phi, not R. Okay. So how to complete the proof now?
Since beta's phi spans the
Right. So see, if it is a 0 or these things, again, you linearity, you will see that alpha of V is equal to 0 for all V belongs to V, because these phi span those things, right? But as is non-degenerate, we have which is contradiction. Yeah. So if you have if you have a W invariant form which is non-degenerate, it is evident that your roots will have their inner product with themselves is non-zero. Okay. Now the more crucial is that we need to prove that phi inverse of alpha check is nothing but 2 alpha by alpha alpha. Okay. How do you go for it? So note that alpha check this is, so alpha check of some B is equal to, so as this is an isomorphism, as phi from V to V star is isomorphism, so there exists V belongs to V such that phi of V is equal to alpha check. Right? And so V will have form. So suppose alpha check of any V dash is equal to V of V dash. Right? Now, so alpha check of alpha, which is nothing but 2. So what you will have? So this is just nothing but, so every vector V, so this is a vector V, unique vector V, you can write down uniquely as X plus C alpha, where X belongs to the hyperplane and C is some scalar belongs to R. Okay, this is a unique decomposition. So alpha check of alpha, which is equal to 2, which is nothing but V of alpha. This is nothing but x plus C alpha of alpha. Okay, but x alpha, this is 0, as this is in hyperplane. This is nothing but C of alpha alpha, which is equal to 2. Right? So what is your C then? So here you can have C as 2 by alpha alpha. Here you can have C is equal to 2 by alpha alpha. Why you able to write down C as a 2 by alpha alpha? Because you know that alpha alpha is non-zero. This is very crucial. Now I claim that V is equal to twice alpha by alpha alpha. Right?
Why inner product of x with alpha is 0?
Why?
Inner
Because
product
x
of
is in hyperplane H alpha actually. Okay. So your V, you will able to write down the perpendicular hyperspace into the R alpha, right? Isn't it?
yes.
Is it clear?
Yes.
And so try to prove that this V has a form, actually see these things. So you came that V is nothing but x plus twice alpha alpha alpha. Claim that this x should be 0. Why is this x is 0? Prove that x with any other vector V is equal to 0 to prove that x is equal to 0. Okay. So let us try to prove it at least. So it will end once and for all what is the thing. So need to prove that this thing is equal to 0. So you take any y belongs to H alpha, you'll have alpha check of y is nothing but x plus C alpha of y. This is equal to x of y, as I mean C alpha is nothing but twice alpha by alpha alpha. This is equal to 0. At second part is 0. So x with all y is equal to 0 for all y belongs to H alpha. And similarly, x with alpha is equal to 0. So that implies that x with all v is equal to 0. So by non-degeneracy, x is equal to 0. Yeah, is it clear? So your inverse image is just nothing but phi inverse of alpha check is nothing but twice alpha by alpha alpha. So we have got this identity. So you can utilize this identity throughout to do the needful. Okay. So good. So at least we have now the correspondence, and yeah. So we have defined while group, some of the examples of those things. Now these are some of the exercises for these things. So first of all, try prove that this is exercise. Prove that there exists prove the to the existence of symmetric W phi invariant form on V. Okay, which is vector space over R. Okay. Now, some like a person from representation theory would quickly say that the existence of invariant WR form actually. How do you get it?
Averaging over.
Yes, you can do it averaging because your Weil group is finite. So suppose as V is finite dimensional vector space over R, there exists a positive definite form on V. So you can simply use you take any basis and you take a standard form actually. Okay, and that's what you have, and that is just nothing but a positive definite form, and you define the new form. What you will define? Complete it. Tell me the definition to have that it as invariant. Anybody from the participants? How I should define using this form, WR invariant, non-degenerate, symmetric form.
Just sum it over the whole.
Weil group.
Sum it over Weil group means, so first of all, you will define the cardinality by the Weil group, whatever these things. And then inside stuff is important for me.
So W in W, WX inner product WY.
Correct. Where W varies or all W, right?
W.
And this is dash. Okay. Yeah. And this will do for you. Okay. So this is indeed check the required form. Okay. In fact, we can do more. So define, so if you have A phi, these are all sigma belongs to GLV such that sigma of phi is equal to phi. Okay. What is the difference between A phi and W? What is the difference, A phi and W phi?
A phi can be larger, right?
Very good. I mean, it is indeed larger. It is actually, see, W is generated by order 2 elements, right? These are reflections. Yeah. And here it is actually any arbitrary, but remember that A phi is again a finite group, okay? Because again, it is contained in S cardinality phi, okay? So that is the thing. So you have yeah. And so you have A phi is contained in W phi is contained in A phi. And so what we have is that if you define, so let another, so first I will these things exercises. Let V phi be the root system. Then so is V star phi check, where phi check is alpha check where alpha belongs to phi. A very important thing. So you will have, suppose you have a root system, then this phi check is also forms a root system. Okay, and exercise is, suppose what is that? That if the form, if I define the form, if I define xy summation alpha belongs to phi, alpha check of x and alpha check of y, this is where xy belongs to V, is symmetric AR invariant, AFI invariant, not only with the W phi, you can extend your form such that it is a AFI invariant actually. So this is again an exercise. Possibly Ritesh will do it for you. Okay. Now, so now we will define what is the direct sum of root systems actually. Here is the definition. Let Vi be vector spaces R with RIB the with RIB their root systems respectively. Okay. Then the direct sum of then the subset, that the direct sum of the root systems Ri is a subset R you define as a disjoint union Ri, which belongs to the direct sum of Vi's. And you often will often write it as okay, very nice and generalizing definition of what you say, what do you mean by a direct sum of the root systems. So if you have corresponding vector spaces, you take those root system, the disjoint union as a as the element of these direct sums of Vi's, and call it as a root system of the ambient space, which is nothing but the direct sum of all the Vi's. Okay, fine. Right. Now, what is a crucial thing is that, I mean, like, so we have already seen the example of direct sum of the root systems. Anybody noticed it?
Yes, for R2 and R.
R2. In R2, we have seen actually the first one.
Yes.
We had seen two, right? I mean, one was so there was one the one with 60-degree angle.
No, that's not direct. This is not a direct sum of root system. In fact, that
Okay,
is
so
an
the R2 with alpha beta minus beta.
right. So example which we have seen this thing is that, so suppose you have 0, and so you have just put it in as actually it's a direct sum, the orthogonal actually perpendicular these things. So this is a beta and this is minus beta. Okay, so this is usually you call it as a A1 cross A1. So this A1 is just nothing but your this thing. It's just nothing but the direct sum of those things. So this is an example of this root system, direct sum of the root system. Okay, fine. Oh, sorry. Yeah. So again, an exercise. These are not very difficult. So suppose if R is or phi, I will just not going to the Bourbakis things actually. So suppose I have already used it as R. In case if it is a too much troublesome, I will change it to phi again. This is phi I. Yeah. Okay. So if phi is equal to, then while groups turn out to be the direct product of the while groups of those things, a very natural thing. So that these things, and now here comes the crucial definition where you call it as a irreducible. A root system phi is irreducible if and only if the action, irreducible if and if it is not a direct sum of two yeah. So you can have phi is equal to phi 1 direct sum phi 2. Yeah. So where phi 1 and phi 2 root system. Yeah. So this is a very natural thing. What is, see, in the coming next lecture, we will see that a very important result, that what you expect as a group thing. So most of you have done a course on the finite group representation theory, right? In case if you have not done, please raise your hand. So some of you have not done the course on finite group representation theory. So at least there are, so those who have rose hand, actually the one who I am assuming they have not done the course. Yeah. Okay. So yeah. So suppose you have What does it imply? That so suppose you have, here is the next result, let us say proposition, is that a root system phi is irreducible if and only if the action of W phi on V is irreducible. Okay. Now this is very important result, very important result. It has a number of applications. And what do you mean by an action of W phi on V is irreducible? So just think that, note that W as a group finite acts on the vector space V. What it is action, which we know that these are, the W is generated by these S alphas. W is just nothing but the S alphas. Alpha belongs to phi. S alpha of V is just nothing but V minus twice of alpha V, twice of alpha V by alpha alpha of alpha. This is because we can write down, we know that alpha check, what is alpha check? This is action. So this is your action, and that's how this V becomes your representation. Okay. Then a representation V of W is said to be irreducible. When do you say a representation at least it is irreducible? Anoy, when you say it is irreducible?
So it can't be written as a direct sum of non-trivial representations.
Yes, very good. So to you, if V, I mean, see, no. So see, irreducible is a different ball game. When do you say it's irreducible? So it is not. It doesn't say that.
Does not have
so
proper.
it says that it does not have any proper sub-representation. So irreducible means there does not exist if there does not such that W is, or W is not a good word, good symbol. Let us say such that V1 is representation of W. That is, W of V1 is V1. So the action of V1 is preserved by, action of W is preserved by these things. So then that's what you say it is a irreducible representation actually. Now there is a very important property that suppose you have a finite dimensional representation of a group, okay, of a finite group over a nice field such that the order of that group does not divide the characteristic of that field does not divide the order of group. Then there is a very famous theorem. Okay. Okay. So what is that name? Somebody will tell. What is that theorem? Yeah. Mushke's theorem. Yeah. What does it say?
B is a finite.
The group has any invariant proper subspace, then it is not irreducible.
No. Could you repeat
V is a
actually?
finite.
Mashke's theorem.
If V is a finite dimensional representation of a group G, and thus the order of group G does not divide the
characteristic of the
characteristic
field
of
should
F,
not divide.
or either of characteristic of F is 0, then V can be written as a direct sum of irreducible representation.
Correct. V can be written as the direct sum of the irreducible representation. Okay. So which is a very important these things. This is a very important thing. So let and V is then V you can write down as a so this result we will use here to show that this is in fact if your root system is irreducible, then this thing. So I will give you a kind of a little task to do it. So we will go back to that result. Suppose phi is irreducible, then need to prove that phi is irreducible. Need to prove that irreducible W module, W representation. Assume contrary, what will happen? Then V you can write down as a V1 direct sum V2. There are some representation did not be irreducible. Of course, with the restriction of the dimension of V, you will always go down and you will have irreducible representation. There is no proper these things. But without these are proper representations of V actually. Okay, so where V1 and V2 are representations P. Okay, now what you need to show that is now, so what you need to show that this thing you just can't have those things actually. Okay, so what is that? So let phi 1 is equal to phi intersection V1 and phi 2 is equal to phi intersection V2. And you need to show that you will be done if you show that phi is equal to phi 1, that is some phi 2, and this phi 1 and phi 2 are root system, which we will continue tomorrow. But just read some of the basic stuff related to the group representation of group theory, and you can yourself complete this proof. Okay, using the invariance of S alphas and these things. Note that V1 and V2 are W invariant. That's what you want. Okay, so we will continue our study of root systems, and so we will have a concrete thing that as while group actually leaves those roots invariant, So there will be a constraint on the angles of the roots and the length of the roots also. So which we will simplify our problem of root system remarkably. And in the tomorrow's lectures, we will continue with that. So we'll meet again in the assignment today. So I will stop here.